Welcome back. Let's continue the review. This here is section 3.9. We're talking about separation of mixtures. Here, the main thing that's going on with this section here is we're trying to get the components of a solution to be separated out. So let's go ahead and put that here. The components of a solution. And what we're trying to do here is we're trying to separate them. Now, the problem with this is that we can't use regular filtration, so you can't put a filter paper into say a funnel and separate it out. So the two ways that we're actually kind of trying to separate here involved one of the two techniques we actually did in class. One of them here was a chromatography. And the other one was going to be a distillation. So I'll put this in a slightly different color here so that this is distillation. So let's briefly talk about both here. In the chromatography section, the main thing that you needed to worry about here for this was that the chromatography involved you using a solution. So let's go ahead and prepare a solution. You had to go ahead and get your volumetric flask, and you had to add to this flask a certain amount of solute. So let's go ahead and say this here, solute. And we'll put a liquid here as well. Go ahead and put a liquid here, put it in blue. And so that liquid here is the solvent. And typically, when we use a volumetric flask, there's a fill line here. And so you want to make sure that you use that when you're mixing it here. But you had to prepare it. In a chromatography, you were asked to prepare a solution of a very specific concentration. I believe we used 0.5 molar NaCl solution and a 1 molar NaCl solution. So the main thing that you needed to figure out is how much am I going to need. So the desired mass of the solute, and let's say that we're going to do this in grams, we had to figure that out, and that was actually derived by using the concentration times the molar mass, and then we multiplied that by the volume that we were going to use, and we're going to use the volume here in liters. Okay, and so when you did all of that here, the big M over here, remember that this is moles per liter, and the mass is in grams here. So what we wound up having here is the liters would cancel, and then the molar mass would be grams per mole. And so here the moles units would cancel, and the only thing that would be left would be the unit here of grams. And so that would be the desired amount. So all you really had to do is figure out the volume. The volume was the size of the container you were going to use. So if you're using a volumetric flask of about 100 milliliters, the volume here would be 0.1. The molar mass would be the molar mass of the solute. So if you're using sodium chloride, I think that's about 58 grams approximately. And then your concentration, that would normally be provided to you, or that's the desired concentration that you want. So you would put that number here, multiply them all together. And that's how you'd figure out how much mass you actually need. So when you do that, all of this information is important. You go ahead and put everything here. So once you figure out the mass, this mass is what comes in here in the solute. You fill it up to the line. So let's go ahead and represent that properly here. All the way up to the line. You would go ahead and put a cap on it, and then you would invert it several times until it all dissolved. And then once you got that, the final concentration of this particular solution would be of that solution concentration that you were after. So if you were after, say, a 1 molar solution, then you would have figured out the mass that you needed for that, and then your concentration here would be a 1 molar. So the next step in this process for a chromatography is that we would then take this information here, and then we would essentially bring this in. So let's kind of put that over here for a second. We would then use that solution, and then we would prepare ourselves the beaker that we wouldn't normally use, and then we would bring this beaker in, and in here we would have a stationary phase, and so that would be the paper that you prepared. And so the stationary phase here would be marked. There would be a starting line here, which is essentially the reference line. And you would add some of this solvent mixture, the solution, you would add some of that here to the bottom. And so let's go ahead and represent some of that here. And so that solute here would be right at the bottom. And so we don't need very much. You would only put in there just enough for the bottom of the stationary phase to get soaked a little bit. But then you would also need to make sure that you added your samples. And so here I'm going to put two samples, sample A and sample B. And once you added that stationary phase to this whole thing, the solvent would then start to climb up, be climbing up the paper here. So what would happen is it will start to climb up, and then it would make its way all the way to a certain point. Depending on when you stopped it, you would let this run up. And when it did that, let's say that it stopped here, that line here between the wet and the dry part here, this is going to be the solvent front. Okay, and each of these lines then would begin to show some kind of separation. And so let's say that the blue one migrated up, and so eventually you might want to see, you'll see a spreading of that all the way up to that point, and it would have spread up like so. The second one would have spread up similar, but maybe the second one only went as far as that. And so you could see that there's a distinction here between them. A actually went a little bit further than B, and so then the question then becomes, what does this mean? What's so significant about this? Well, it all depends about what's inside the solvent, and we're usually trying to figure out what's going on with these samples. But so there's a couple of scenarios here for the solvent. So if the solvent, there's two scenarios. One, either the solvent here is going to be polar, or the solvent is going to be a non-polar solvent. So let's take the first example here. What if the solvent here is polar? Well, if it's polar and we saw this arrangement, then we would say that because A traveled the furthest up here to very high, the distance or the length traveled here, A is actually more polar than B. And so that would be what would be happening there. And if it were the other way around, if we do the example here for the solvent is a non-polar solvent. And so that would then, let me change it here. That would then put the scenario here that if A traveled the furthest, then the A would be more non-polar than B would, because B didn't travel that far. So it all depends on what the solvent is. So you need to be attentive to that little detail when you're trying to answer these types of questions. So other questions that you might encounter here would be related to the solution that was prepared. So I'll just go backtrack a little bit here and go back, and let's talk a little bit about this particular section here. So let me make some room for myself. Bring this over here, and then let's focus on this. I'm going to go ahead and move that over that way. Bring this over here to this side. And one thing that I want to tell you here is that what happens if you overfill the solution past this fill line? What if you actually come up here and you fill it up above it? Well, keep in mind that that's actually going to be more volume that's in the container relative to the solid. So if you fill it past the fill line, that would actually give you a lower concentration. On the other side, if you were underfilling it, then that would actually give you a stronger concentration, because the volume is actually not as high as it should be. Remember, the fill line is accurate to give you the exact volume that this container is going to have. So you always want to fill it to the fill line. All right, so that addresses the chromatography section. So let's go ahead and talk a little bit about the distillation. So the distillation part was mostly covered in class in terms of concept. And so the concept there is going to be related to taking advantage of some of the colligative properties like the boiling point. That's really in the one for the distillation, that's the one we're going to be looking at the most. So distillation. And here, let's say that we have some kind of compound A versus a compound B. And then we have another one here, compound B. If we had, say, the boiling point of this one, let's say that the boiling point was at, let's say here 90 degrees Celsius is equal to the boiling point. And let's say that the compound B had a boiling point of, say, 70 degrees Celsius. Well, what we want to be able to do here is to use these in the apparatus. And so if you recall, the apparatus looked something like this. Let me go ahead and draw it, and then I'll bring it back here in a second. Okay, so here's the distillation apparatus. I haven't drawn everything on here. Remember, there's clamps all the way around at each individual place. So you would have a clamp here, a clamp there, probably a clamp here at the top, clamp here, clamp for this piece, that piece, and the bottom here, the round bottom flask. Now, it's important to know the general pieces of how they go, but one important piece that you should be aware of is the green dot over here at the very top. that green dot here at the very top, that there is the thermometer. And so that thermometer there will have a sleeve on it so that nothing can escape from it. There's actually like a little rubber sleeve that goes on top. Or it could be a rubber stopper, either way. And so what will happen here is if we have two compounds, let's say that we're going to say compound is actually colored green. And so we would have here, we would have compound B here. Let's say B is, or compound A is red and compound B is green. And so you've got a heat source. And so let's just put that down here at the bottom. And that could be a heat, just a hot plate. It could be a Bunsen burner. Maybe you put the round bottom flask in some sand and heat the sand. And then that in turn, through conductive heating, will heat up the solution on the inside. But no matter what, though, you've got some heat being applied. And that heat then will radiate out into that container, raising the boiling point or the temperature of these substances inside. And when those substances are heated, then they're going to start to essentially begin to boil. Now, since we know that one of these is actually boiling at a lower temperature, 70 degrees for the B, relative to compound A is at 90, so clearly B would boil first. And so what will happen here is that the compound B would then start to enter the gas phase. And it would travel up the column here all the way to the top. And it will kind of pull itself here at the very top in this section here, up until there's enough there that there's an accumulation of that. Some of it may come back down, but probably the most likely scenario that's going to happen here is it'll make its way down this portion here down the bottom. And so when that does, notice that because it isn't an evaporate, it's in a gas form, a lot of that evaporate, which is in a vapor, will come up here. And what's happening here through this is you're going to have some water coming in. It'll go through the inside of this container, which is essentially think of it kind of like a tunnel within a tunnel. So there's this path on the inside, but the water is able to kind of accumulate on the top all the way around, and it will slow down this evaporate. The kinetic energy will then start to get lower, and so it'll start to condense here, and it'll start to make its way down as it leaks. Now, the water obviously comes out there, but it'll accumulate in liquid form, and then it'll come in here and eventually start to pull inside. So the end product here at the very end, here, we've essentially isolated compound B at the lower temperature. Now, what this looks like graphically, so you want to make sure you pay attention to that. So part of the graphic here would be that you would have, at the bottom here, you would have a temperature increasing here, and then the volume would be measured at the bottom and increases to the right. And typically, if you want to color code these, you would find at a certain temperature and volume ratio, you would find to see several points would come here that would correspond to the first compound, which would be B. And then you would find for the other compound, there would be a break here of it. So you'll see some points collected there. And then you'd have for the other compound, you'll see it come up here. So this region here, so that would be for compound B here. And then the top part over here, this here would be for compound A. So you should be able to field questions there about which temperature range is appropriate to distill compound A, compound B. All you really need to do is extrapolate those points over here to the graph in either case. So this would be the region here for A. And then if you did the same thing here for B, you could see that the region down here would be for compound B. And so the top one here would be for A correspondingly. So those were the main things that you needed to be able to do here for this particular section. Most of the questions, at least for the exam here for us, would be concentrating on theory for the distillation, knowing the procedure for the chromatography. But for the AP exam, you should also be able to explain and how to do both. And so that pretty much covers things here for section 3.9. We'll continue the review here in the next video, looking at section 3.10 solutions. See you then. Okay, and then we